your other Gen Chem professors and asked whether we covered the Born-Haber cycle, which is really cool, and I may mention it briefly, but we won't cover it and you won't have to work problems with it. But it's a great example of use of Hess's law. So let's talk about what we've got going on. So our last thing here, you've got whatever's going on in lab, but we have a final exam. Final exam on Friday next week. Actually, I'm going to give you a homework because you haven't had homework on Hess's law yet, and that will be on the final exam. So homework due Monday morning. You guys want to pick something else? I know you have finals, yes. Sure, we'll do it Wednesday. Homework due Wednesday morning. Okay, so hopefully that's a little bit, you can work that in with your final schedules. But the problems that are going to be on this homework, I'm going to pick things like they'll be on the exam. All right, so so do make sure you do it and take it seriously, ask questions and all that sort of stuff. I'll be available, help by appointment. I don't really have a schedule for next week, so if you can tell me, let me know when you'd like to come in for help, sending me an email or something. I can try to come in, or we can work out some sort of mutual time to work on things. So if you want help, please let me know. I'll also run a help session on Thursday evening at the usual 7:30 p.m. On Google Meet. Our final exam on Friday is going to be 8:30 to 11:30 p.m. is when it is, not p.m., a.m. Is when that final is. I will start at 8:30, and I'm not gonna. I think I said this before. I'm gonna write like 1.5 times the final, right? So it's gonna cover things a little more heavy emphasis on things since the last exam, and then it goes across the whole class. So can expect it to be about 1.5 times as long. Questions on stuff we've got going? Okay.
Will there be like a practice?
I will, yeah, I'll get up a practice final exam for you. Send me an email if you don't see it by a couple days. Okay. If you don't see it by Monday and you want it, send me an email. Okay, so this isn't a problem we were doing before. We were using Hess's law. Remember, what Hess's law is about is that it's about state functions, right? So the energy, the enthalpy of reaction, and lots of things about reactions, but we're only concerned with enthalpy today. Next semester we'll be concerned with other things. But enthalpies of reactions, which is a change in enthalpy with reaction, are state functions. So what that means is they don't depend on path. Which means all we care about is the beginning and end conditions, and so it means we can treat these things like math equations, and we can do algebra to them, and we can add them up to make whatever we want. So I can take a series of equations, and if I can flip them around, and things like that, I can get whatever sort of answer I want. So what can we do to these equations? So we can flip equations. And then we're going to change the sign on heat or on enthalpy. So delta H. Delta H is enthalpy. I'm typing it so I don't have to go up and find the symbol thing and that. But it's delta H is that. So we can flip those equations, but we need to change the sign. We can multiply the equations times a number, but we have to multiply the energy too. So times a number, and that includes the enthalpy. Okay, so just like in algebra, you can multiply one side times 5 as long as you multiply the other side times 5. And then we can add these together. Add or subtract reactions. Okay, so these are our tools. So last time we ended up trying to take this equation right here. We're trying to make the equation up above. So how this is really useful is if I don't know what the enthalpy of this reaction is, and I have the enthalpies of all these reactions, if the problem's been set up correctly, I can take these reactions and I can do this flipping and multiplying and adding, and I can get that reaction. All right, so last time, we just talked about this and gotten a little ways in, and we decided that the bottom reaction, we don't flip this one, right? Because the CH4 is a reactant here and it's a reactant there, okay? The CO is a reactant here and a product there, so I'm going to flip that middle one. Okay, so I'm going to rewrite that one. I'm going to write it as 2CO2 goes to 2CO. I'm not going to worry about the phases, right, until we're done, plus O2. And since I flipped the reaction, that means that I have to make this plus 566.0 kilojoules, right? Okay? And then this top one, hydrogen gas is a reactant, right? And hydrogen gas is a product, so I'm going to have to flip that one. So that's going to become 2 water goes to 2 H2 plus O2. And so plus 483. Whoops. I have to flip the sign on that. All right, so now I'm going to go ahead and put, you guys check my work. I didn't copy anything wrong, hopefully. But so now I'm going to cross out those two light reactions because I've gotten them, but I want to see if I'm going to be able to get everything to cancel out or make the things I want. So if I look at this one right here, you see I have 2 H2 and I have 3 H2, right? So that's not going to work the way it is, and there's no other place that H2 shows up, right, on its own. So this needs to become a 3H2, so I can multiply everything times 3 over 2. So if I multiply 3 halves, right, times that, 3 halves, and 3 halves, okay, what I'm going to get is these 2's cancel, and I'm going to have a 3 halves O2, oh goody. But that's going to give me 3H2O goes to 3H2 plus 3 halves O2. And I have to multiply this heat also by 3 halves. I can't do that one in my head. Those of you that have my calculators, bring them back up at the end, please. But let's see. So I've got 566 times, no, that's not the one. It's the 483, right? The 483.6 times 3 divided by 2. So now it's 725.4 kilojoules, right? Okay, and so now I'm going to go ahead, I'm going to put a line through this one because I don't want to confuse myself that I need that one. Let's look at the other one. So the other one's got, I need one carbon dioxide on the other side, carbon monoxide on the other side. And this equation that I haven't changed has no carbon monoxide. And this equation has no carbon monoxide. Is that right? So I'm going to have to get one carbon monoxide over here, I'm going to have to multiply this by 1/2. All right? So we're going to go ahead and do 1/2 times that, and 1/2 times that, and 1/2 times the oxygen. Maybe the 3 halves oxygen will work out nicely. Anyway, so I'm going to go ahead and I can cancel, the 2's will cancel, right? 2 divided by 2 is 1. 2's cancel, and I'm left with 1/2 oxygen. I'm going to rewrite it down here. So now I've got 1 carbon dioxide goes to make 1 carbon monoxide, plus 1/2 oxygen, right? And my delta H here is going to be equal to half of what it was above. I think maybe I can do that. What is that? Maybe I can't. 8, 250 plus 8, 258? Is that right? No. Yes. Somebody do that in their calculator and tell me if I was wrong in my head. If I multiply 283. Yeah, that makes sense. Okay. Thank you. All right, so 283. All right, so I've now got those working, and we didn't flip the other one. And in looking at the other one in terms of, do I need to multiply this by anything? I have 1 methane and 1 methane, so I'm not going to do anything to it. And now I'm hoping by the magic of chemistry and the magic of that somebody set this problem up for us, that everything's going to work out well. Okay, and then our free energy change, or not a free energy change, but our enthalpy change here is going to be negative 802.5 kilojoules. Okay, let's go. Now comes cancellation and adding. So we're going to add this whole thing up, and then we'll cancel things that are common. So all my reactants here are water and carbon dioxide and methane and oxygen. So I'm going to put those all on one side of the equation right here. So I've got that 3 water plus a carbon dioxide plus a methane plus 2 oxygen gas. That's going to go to make everything on the right side. So all the products. So 3H2 plus 3 halves O2 plus CO plus 1/2 O2 plus CO2 plus 2H2O. And I'm going to add those, I'll add those enthalpies up in a second, right? Let's see if we get the equation we were after here. So if I take this 3 halves O2 and 1/2 O2, what does that add up to? 4 halves O2, right? If I take these two together and I add them together, because they're both on the same side of the equation, I get 4 over 2O2 or 2O2, right? 4 divided by 2 is 2. You guys okay with that? Okay. So I've got a 2O2 there. Anything else where I have the same thing on the same side? I don't see anything else. Okay. So now let's try canceling some things. So let's see. So do you see I have 2O2 here, right? And I have 2O2 here, so those cancel. All right. I have 1 CO2 here, and I have 1 CO2 here, so those cancel. All right. And then I have everything else. I have 3 waters here and 2 waters here, right? So these waters go away, 2 waters there, and this becomes 1 water, right? Because I have 3 waters and 2 waters, so I can subtract 2. And what I'm doing is I'm just canceling, but I'm doing algebra. I subtracted 2 waters from each side, and I have 1 water left on this side. Okay? It's just like what you would do with equations in math. All right, I'm going to rewrite this now, make it less messy. So I've got an H2O plus a CH4 goes to 3H2 plus the oxygen's all gone, CO, and that's it. Yeah, that looks like that's it. Was that what the equation up above was? I hope it is. All right, so we've got, that's not the equation.
No, it's right, it's just out of order. Yeah, it's out of order.
It's the same thing. Yeah, I was looking at a different one, sorry. But you're right. Right, so we've got, do you guys see? So we need a CH4 and H2O as reactants and a CO and 3H2. Okay, and that's what we've got, H2O, CH4, 3H2, and CO. Okay, so now and what I can do and what I haven't done yet is I haven't added up the enthalpies. So these were the enthalpies for our reactions right there after we had flipped signs and multiplied by the coefficients we needed to get everything to cancel to add up to the reaction we were looking for. 0.72.5 plus 2, yeah, sorry, 4 plus 283, 0 plus, 0 minus 802.5. Okay, so I got, somebody check my calculator on this. I've made an error at least once while doing that. 205.9 kilojoules, and I've got it as positive. Is that what other people got? Okay, good. That's great. So you see how we did that? And so where this is super useful is it might be hard. This actually isn't a hard reaction to measure measure that, but you know, it could be that this would be a really hard reaction to measure the enthalpy change for, but I could measure all these. Or somebody else had already done these. And so I could use that to figure that out. All right, I have 5 minutes left. I will not have time to talk about the Bohr-Haber cycle at all, but I will have time to talk about enthalpies of formation. So this is where this is really, really useful. All right, we can figure out all these reactions using the enthalpies of formation. So the enthalpy of formation is the enthalpy calculated, it's really measured, for a compound being made from its elements. So let's take this. So it's called a standard enthalpy of formation because it's under standard conditions. But actually down here, we mostly have the enthalpies of formation here for this. So if we look at this reaction right here, we've got zinc oxide, right? And what the enthalpy of formation for zinc oxide would be is, it would be, so I'm just going to take this as an example, is we'd take half, this would be the molar enthalpy, half a zinc oxide, not half a zinc, just one zinc, plus 1/2 oxygen, because I only need one oxygen, right? One oxygen gas, because that's our standard, to make a zinc oxide. That is the enthalpy of formation, okay? And what we would do is, so we can do that, and we can make a whole bunch of these enthalpy of formation reactions, and we can add them up. So we can look up, all these enthalpy of formations are in a table, right? They're in your book. We're going to look them up right now and look at them. But I can look all these things up in a table, and then I can make any reaction I want, as long as the enthalpies of formations for my compounds are there, because I can add them up like we just did with Hess's law. Now, we're not probably going to have time to work a problem, and so I may make an extra video and post it, because this is a pretty important concept. But let's look at the table. So it's Appendix B. What was that, problem 94? Let's look this up in your book. I didn't paste it in because it's enormous, because it has lots of different compounds in it. But if we go over here and we look in your book, we're in energy, and we go into the chapter. Hopefully Achieve doesn't let me down. All right, so that was 94, was it? I just want to be able to click on the link to get to the right part. Oh, am I looking at the answers? No. Where's 94? Oh, there it is, right there. No, that's not right. It wasn't 94. You guys let me down. What was it? 98. There we go.